Now we will see what we can do if we have a warped element. So the usual approach is perform a warping correction. If you have a flat element, but you want to model a warp geometry by using a flat element, then you do a correction. It's approximate, but again, if you increase the number of elements, you will reduce the amount of approximation. So we said that the warping is the case if 4 nodes of a quadrilateral shell element do not lie on the same plane the element is warped. So let's say that I have a coordinate axis as follows: global coordinate system x, y, z. Let me draw the midplane first. And I will just draw the nodes as follows. So this one is the warped shell element. And this one is the projection of the element to a flat mid-surface. Okay, so let's call these nodes as node 1, node 2, 3, and 4. And the projected nodes, these are the nodes at the projected plane, as A, B, C, and D. So I want to move this one to here. Okay. So we'll say when flat elements, flat shell elements are used to model warp geometries, the following procedure is utilized, let's say. Step 1. First, calculate the coordinates of flat projected plane. Flat projection plane. So in other words, I need the coordinates of points A, B, C, and D. This can be done by calculating the rotation matrix using approach 2. Okay, and then so x, let's call it A, will be equal to rotation matrix multiplied by the coordinates of the first node. Okay, so these are the original nodal coordinates. So rotation matrix obtained with approach 2. If you remember, the approach uses V13 and V24, and from that it generates a coordinate axis for the midpoint. Now by multiplying the xyz coordinate of point 1 with the rotation matrix, I'm actually calculating the coordinates of point A, and if I repeat the same procedure for A, B, C, and D, I will be defining a flat surface, right, flat plane, and the coordinate axis of the flat plane will exactly be the same as the midpoint of the warped element. So since I have a flat plane, so we have xa defined as x coordinate, y coordinate, and z coordinate. Of course, when you do that, the z coordinate will not be equal to 0. We will deal with that later, but we will be using the xa and ya as the x, y coordinate of projected element. So basically what we are doing is we are calculating the stiffness matrix of, we have a flat shell element defined by points A, B, C, and D. Okay, and the coordinates of xy coordinates of this flat shell is determined as follows. But of course, when you do that, you will see that at every node you have a z value. It's not equal to 0, and at different nodes they are not equal to same. But what we know is projected flat plate projected flat plane is at the mid surface. Okay, we just calculated the flat plane by using the coordinate axis of the mid surface. Okay, thus the distance of each node to the mid surface in the local 3 direction of the shell element is the same and equal to D. And D can be calculated as D will be equal to ZA plus ZC minus ZB minus ZD divided by 4. So here we are saying that, remember that these flat projected plane and this warped element, they all share the same midpoint. And in the local 3-axis direction, if you measure the distance, you will see that that distance will be equal to D, and you can determine the value of that D with the following operation. Okay? All right, now we know what D is. We know what this one is. I can calculate the element stiffness matrix for this flat plate. But remember that the original nodes are here. We obtained the stiffness coefficients on the projected plane. So in other words, I have the stiffness coefficients for these translations, but they have to be in this location. So what I need to do, I need to transfer the forces and moments defined in the flat plane to the original locations. Now let's take a look at how we can do that. So let's show a figure, just one edge of the member. That's point A. That's point B. We have point 1 here. We have point 2 here. This is 1 and 2. And that distance is D. That distance is D. Now, if you take a look at the membrane forces at point A, so I have Fxa and Fxb. Sorry, this should be Fya. And here also I have Fxb and Fyb. So if you want to carry these forces to that node, you will see that these forces will create additional moments here. You have a force and the moment arm, right? So we are saying that the axial or membrane forces at the projected plane will create additional moments at the actual location of nodes. Okay, so here we are you can just think of it this way also. The displacements at node B will create additional rotation at node 2. So this is nothing but the definition of a constraint equation. You are relating the degrees of freedoms with other degrees of freedoms. right? We want to relate the degrees of freedom of node B with the degrees of freedoms located at node 2. So you can use a transformation method for that, and for this purpose you need a relationship. You can write this relationship in terms of displacements, or you can write this relationship in terms of forces. Now here I will just write it in terms of forces. Then delta my, the additional force due to this eccentricity, will be equal to the force in the x direction multiplied with the magnitude of the eccentricity, which is equal to d. So you can do the same thing. You can say that likewise axial translations of the projected plane will create rotations at the actual location of nodes. That is at 1 and 2. So you can just write a relationship in terms of axial translations and the rotations. So these additional moments and rotations can be incorporated with the transformation matrix. So if you think about it, what we are doing here is nothing different than the axis transformation for a frame element. Okay, now I will put that example video also online. So this is a different version of it. Instead of having 2 nodes like in the frame element, here we have 4 nodes. Now I will write the relationship with forces as follows. So F 1, 2, 3, 4. So this represents that F in the actual locations of the nodes will be equal to a transformation matrix multiplied by the F at the projected plane. So let's call this one equation plus, and I can write the same thing for the displacements, and when you do that, the relationship for the displacements are just equal to the transpose of the transformation matrix. So U1, 2, 3, 4 will be equal to U at the projected plane. So by using, let's call this one double plus. We can show that the stiffness transformation, so the stiffness at the original location of the nodes are equal to T transpose times KABCD, stiffness matrix of the obtained for the projected plane multiplied by T. This is the stiffness matrix for the warped element. and this is the stiffness matrix obtained for the projected plane. And then once we have the element stiffness matrix for the warped element, in order to calculate the shell element in the global coordinate system, you just again perform the coordinate transformation by using the stiffness rotation matrix obtained by using the second approach. Okay, so what will that T equal to? So we can write T as equal to 1, 0, 0, 0, and D. So this tells that the translation in the x direction will create additional moment or additional rotation in y direction, and this one will be 0 minus d and 0. Here translation or force in y direction will create a negative moment in the x direction, and that's it. The rest will be equal to, we have the drilling of here, all equal to 0. Okay, and this part is 0 also, and you have the same type of transformation for other nodes. This portion is transformation from A to 1, and you have the rest of the transformation matrix obtained in a similar way, and this will be a 24 by 24 matrix. Now let's take a look at the implementation of the flat shell element. Now we will have the warping correction here also. Now this flat shell element is constructed by using the membrane element with drilling degrees of freedom, an enhanced version of what we discussed, not much big of a difference. And a 4-node thick shell element is the Adnan Ibrahim Begovic PQ1 thick plate element. So the only difference here is now we have 6 degrees of freedom at every node, so we do the number of equation by assigning 6 degrees of freedom at every node. Now the important thing here is the warping correction. Now, as we discussed, we obtain the rotation matrix, and rotation matrix is obtained by using the coordinates of V12 and V13, and we obtain the U1, U3 and U2 directions as follows. And for this case we get a rotation matrix, and we say that by multiplying the coordinates of each node by the rotation matrix, we obtain the coordinates of the projected plane. Okay, so this is what I'm doing here: original coordinates and the rotation matrix. So I'm multiplying just getting the elements coordinates into that, and then multiply it with the rotation vector, transfer it to xy, and I'm just only taking the x and y coordinates and put it in another array called xy. And then by using this, okay, so this I'm just putting all the full 3 nodes, coordinates of the nodes into this array. This array will hold only the first 2 x and y coordinates. I'm transferring it to the twist, this form, this subroutine, and this subroutine will calculate the d distance, the eccentricity of each node, and we discussed this equation, and then from that it generates the transformation matrix here. Okay, now the other thing is the calculation of the rotation matrix. Now here I'm calculating V12 and V13. So let's remember V12 and we have the V13 vectors. So when you take the cross product of V12 and V13, you calculate your Vz vector, and dividing it with its length, I'm obtaining the unit vector. Here there's a calculation of V12, but we are not using it. So V1 is just V13 divided by its length. So we have should correct this. This confuses me. This should be V13. This should be V24. And this is our V1 direction. This is the V3 direction. And then V2 is simply calculated by cross producting V3 with V1 and this way. And this is something related with the MATCAT. I'm just putting these vectors in the column wise and then transferring it to the transpose of it, so that rotation matrix is formed as follows: L1, M1, N1, okay. And then I have this mapping. Now the membrane element will give me a 12 by 12 matrix. So these are the locations, new locations of each degrees of freedom. So by using these two mapping vectors, I will be doing the assembly. Now we have the form global stiffness here. So I'm calculating the rotation matrix for each element. And then I make the coordinate planar. So from XYZ, I get the XY of the projected plane, and as well as I get the transformation matrix. Now I'm preparing a 24 by 24 rotation matrix here. So I'm getting the element stiffness matrix for the membrane action, element stiffness matrix for the plate bending action, and by using the mapping that I show in here, I'm creating two new matrices. This is the not new matrix but the shell matrix. I'm just putting this into the new 24 by 24 matrix by shuffling the locations of the coefficients according to IMEMB, and I do the same thing for the plate element. Now I have the 24 by 24 shell matrix, but this is for the projected plane and in the elements local coordinate system. So the first thing that I do is from the projected plane to the warp geometry, this transformation, and from the warp local geometry to the global geometry of the system, I have the coordinate transformation here. After doing that, I will just assemble it to the structural stiffness matrix. So the only difference here is this is the from membrane to shell mapping. You feel the shell stiffness accordingly, and then warping correction. So let's write it. This one is warping correction. And this one is rotation to the global coordinates. Just write two global coordinates. and afterwards you perform the solution. Now, as an example case, I will be using the twisting beam problem. This is a benchmark problem given in the literature. So you have a beam and then you give a small angle at every mesh point, and then you have a twisted beam, and then you apply an out of plane load and an in plane load and check it with the analytical results. So here the first thing that I'm going to do is to show what we were doing for this, just for the fifth element. This is 0, 1, 2, 3, and 4. So these are the coordinates, x, y, z coordinates of that element. Now we calculate the rotation matrix. The rotation matrix is calculated again. Let me draw in this way. So the unit vector should be something like that. Okay. And then this is the coordinates of the first point. Okay. 3, y, and z coordinates of the first point, of this point. I'm multiplying it with the rotation matrix and I'm getting its coordinate in the projected plane. So these are the coordinates of point A, coordinates of point B, C, and D. So as you see, I also have some z coordinates here. Remember that these coordinates are the distance to the, we have the z coordinates, sorry, and their distance is calculated with this formula, and I obtain the eccentricity. The distance to the mid projected flat plane is equal to 0.018. Now the solution. This is the nodal coordinates of the whole structure. Connectivity matrix. Restraints, I have the in-plane loading and out-of-plane loading. Thickness, material properties. So for the in-plane loading, I do the solution, and the tip displacement that I obtain is equal to 0.0057, and the analytical result is 0.54. So this is a very close result, assuming that at every angle for the warping corrections that some sort of approximation is involved. But this is a very nice approach for this very difficult problem. And for the out of plane loading, the displacement that I get is 0.002, and the analytical result is 0.017. So even with this flat shell elements, with this simple warping correction, we can actually solve a very complicated, very challenging problem like this.